Velocity time graphs are one of the easiest ways to lose marks in exams. What we're going to have a look at in today's session is how we can break these graphs down to read them easily, understand how we can calculate acceleration and how we can calculate distance travelled. Let's start off with a nice clean example. So before we get started, you can download a worksheet to accompany this lesson so you can work alongside with me. If you have a look in the description below, you'll see a link to my website where you can download this. Now we'll break our graph down into three sections. If you have a look at region A, we can see that time is elapsing as velocity is increasing. Now this means that our object is accelerating. Now because we've got a straight line, this means that acceleration is constant. Now region B, you can see velocity isn't changing. So this is an object moving at a constant velocity of 20 meters per second. And then for region C, we can see that velocity is increasing again. Now again, it's a straight line, so we know it's a constant acceleration, but have a look at the gradient of region C compared to region A. You can see that this is a shallower gradient, so it means it must have a lower acceleration. So let's move on to actually calculating some accelerations. As we said a moment ago, if you calculate the gradient of a velocity time graph, you'll be able to calculate the acceleration of our object that's moving. So as you can see on a graph here, we're putting on a standard gradient triangle, and I'm just going to move across the visualizer so you can see me working out the acceleration of this object. Okay, so let's have a go at calculating the gradient of regions A and region C. I'm going to do this in pen just so it stands out better on the video, but if this is a real exam, definitely do it in pencil just in case things go wrong. Now the key with this, make sure you make a nice big gradient triangle. I always like to label the values on my triangle and then we can work it out in the space below. So we can actually make our triangle really big for this one. So let's put some lines in, hopefully they're nice and clear. Okay, so remember, of course, for gradient, we're looking at the change in y divided by the change in x. So I'm just going to measure off my points here. So this is 20 and this is 0. And on the x-axis, this is 10 and this is 0. So my change in y is going to be 20 meters per second. My change in x is going to be 10 seconds. So what this means now is that if I want to work out my acceleration, it's equal to our change in y over the change in x, which is going to be 20 divided by 10, so that equals 2 meters per second squared. So let's come back and have a look at region C. Again, I'm going to try and draw on a nice big triangle, as big as I can on the shape that I've got. So it looks a little bit like this. And again, it's always a good idea just to measure these values off the graph. So that's 14, that's 20, that's 25, and that's 20. So if we look at our change in y, this is going to be 25 minus 20, which is 5. If we look at our change in x, this is going to be 20 divided by 14. So come back to our acceleration. So again, it's our change in y over our change in x, which is 5 divided by 6. Now we can't leave our answers as a fraction, so let me just get my calculator. And this gives us 0.83 meters per second squared. Lovely. So we're now going to move back and have a look at how can we use these graphs to work out distance travelled. Working out distance travelled by an object with a velocity time graph is nice and easy, because what we're going to do is we're going to look at working out the area between the line and the x-axis. Now you notice this is a pretty hideous shape, so what I've done is I've actually broken it down into much more manageable lumps, and so what we'll do is that we'll work out the area under this section for region A first, then we do for region B, then we do for region C, and then finally we just add it all up, and that will be our total distance travelled. So let's move back to the visualizer and see how that works for this example. We'll do this a region at a time, so we'll break down our graph into some nice shapes. We'll go for triangles and rectangles because we know how to work out the area of those for maths. So let's just start off by doing region A. So what we've got here, we've got a nice triangle. So obviously if I'm working out the area of a triangle, we know the area of a triangle is going to be a half base times height. So let's have a look at some values on here. So this will be a half times by 10 times by 20. So 10 20s are 200 times by half will give us 100 meters. So that's our first section. Now region B will do exactly the same thing. I'm just going to change colour so it stands out a little bit. Now of course this is a rectangle this time, so we're going to be doing base times height for this area. So base times height, and the base in this case is 4 seconds, and the height is 20 seconds, so 4 20s are 80 meters. Now for region C, we've got a slightly awkward shape here. Now you can actually use the trapezium rule if that's something you're comfortable with, but to be perfectly honest, I think we'll break it down into a rectangle and a triangle. So we've got those shapes there. So if we do the rectangle first, that's a nice easy bit. So again, it's our base, which is 6, times by a height, which is 20. So this little bit here will be 120 meters. And then this section here, our triangle, again, it's a half base times height. So that would be a half times by 6 times by 5. So 6 5s are 30, times a half is 15. So what we know is that region for C is our 120 meters from the rectangular bit plus the 15 meters from the triangular bit. So total distance for region C will be 135 meters. Now our final job is we're just going to add up all of those individual sections. So we've got 100 from region A, plus 80 for region B, plus 135 for region C. So what's that? 235, 315 meters. So that is our total distance travelled for that entire graph. But again, the key to this is break it down into sections and then work out the area of each of those individual sections. As always in these videos, I like to give you guys the chance to have a go at something for yourself. Now obviously we've just worked through a couple of examples, so you try this one for yourself and see what happens. So what I'd recommend doing, start by trying to work out the gradients of region A and region C. That will give you the acceleration. Notice with region C, this is a downward slope, so this is going to give us a negative acceleration. So this is going to show something that's slowing down. So try that first and then have a go at trying to work out the area under this graph to work out the distance travelled. Again, best way of doing it, break it down into some shapes. So you've got a nice little triangle for region A, nice rectangle for region B, and you can break region C down into a little triangle and rectangle. So have a go at that. We'll come back in a second and see how that goes. So pause the video here and we'll be back in a sec. So I hope that went well. We'll start off by doing some accelerations. So let's have a look at region A first of all. So again, we're going to put our nice gradient triangle on this and try and make it as big as you possibly can. Now I've chosen the numbers for this graph so that it's easy to read off the axes. So again, we know that we're doing a gradient calculation, so my gradient, which will be my acceleration, equals my change in y over my change in x. So again, we can read the points off the graph. It'll just help us do that a little bit easier. These ones are okay because they're sat on the x-axis, so you've got lots of zeros involved, but it's particularly ones like C where I like to put those values on. So in this case, we've got a change in y of 12, a change in x of 6, so this will be 12 over 6, which gives us 2 meters per second squared. So let's move across to region C. Again, draw yourself a nice big triangle. So reading off the values of our graph, so we've got 12 here, we've got 4 here, and so that means we've got a change in y of 8, and then our values off here are 16 and 10, so that's a change in x of 6. Now because this is downward sloping, technically this is a change in velocity of minus 8 meters per second because it's getting slower, and that's going to give us our little minus sign that we require to show that we've got a negative acceleration, it's slowing down. So once again, my acceleration is the gradient, so it's that change in y over the change in x, so that's negative 8 over negative 6, so it's going to give me 1 1/3, isn't it? So 1.3 meters per second squared. Now because it's physics, we tend not to use a recurring symbol, so we tend to round it, don't forget the minus sign. So in this particular case, I'd be quite happy leaving this as 1.3 meters per second squared. Hope that went well. Let's have a look at checking the second part of this, which is our distance travelled. Now I'm using a clean version of this just because I had all my working from the gradients on and I don't want it to get too cluttered. First thing as always, break this down into our shapes. That's always a nice thing to start with. So I've got region A is a triangle, region B is a rectangle. Have a look at region C. I'm going to have to break this up into a triangle and a rectangle. And so essentially all I do now is work out the area of these 4 little bits, add them all up, and that will be our total distance travelled. So triangle for region A, so it's going to be a half times base times height, so that's a half times 6 times 12, so that's 72. Half of 72 is 36. And then the next bit, we've got this rectangle here, so this is going to be 12 times by 4, which gives us 48 metres. And then this bit, we're just going to break it down into this triangle and rectangle. So let's do the rectangle first. So that's 6 times by 4, which is 24 metres. And then finally, we've got our triangular section here. So just be a bit careful when you read this off. So this is 12, and this is 4. So the height of my triangle is going to be 8, and the base of the triangle is from 10 to 16 seconds. So we've got that. So what's that? 48. That's 24 metres. So the next job will just come down below, and we'll add all of these up. Let's add these 4 little bits up together then. So region A was 36 metres, region B was 48 metres, and then region C with these 2 sections are 24 and are 24 metres. So if we add those all up, we've got 60, 100, 108, 128, 132 metres. So that's our total distance travelled by this object. So this is quite an interesting one just for us to finish off, because what we're seeing here is we're seeing that this is definitely velocity. We know velocity is a vector quantity, we know therefore direction is important, and we can see that from the graph because we've got both positive and negative velocities. Now what we're going to have a go at here is we're going to have a go at some distance calculations, because it's quite an interesting one here. We've got these regions that we can break up between the line and the x-axis, but from this, once we've worked out distance, we can also work out the displacement. So that's our distance from the very start to the very finish in a straight line, and our velocity time graph allows us to do that. So let's try and see if we can make that work. So with something complicated like this, I always think the best thing to do is to actually just try and visualize what's happening in terms of the motion of this object. So to begin with, let's say it's moving to the right at 10 meters per second, and then after 5 seconds it starts to slow down till it gets to rest at 10 seconds. Now at which point we can now see that the velocity is negative. This now means that it's moving in the opposite direction. So it started moving to the right, it's now moving to the left. And we can see that its velocity is now increasing to -6 meters per second to the left. So we're seeing some acceleration here. And then it reaches a new constant velocity of -6 meters per second. Again, that means it's moving to the left. So this object starts off moving to the right, comes to rest, stops, and then it moves back to the left again. Now what we can do, just like before, we can break our graph down into triangles and rectangles, work out the area of each of these triangles and rectangles, add them all up, and that will be our total distance travelled. So for this one here, it's a rectangle, so base times by height, so 5 times by 10 is 50 meters. This one here is a triangle, so again a half base times height. So we've got a base of 5 seconds, and we've got a height of 10, so that gives us 25 meters. This here is a triangle again, so it's a half base times height, so a half times 3 times by 6, which gives us 9 meters. And then finally we've got our rectangle here, so again base times by height, so 7 times by 6, which gives me 42 meters. So my final job, I'm just going to add up all of these distances that we've just worked out. And that gives me 126 meters. So that's our distance travelled, because it's the area between the line and the x-axis all added together. I'm going to show you a little trick now for how we can use this to work out our displacement. Let's just remember what we've seen already. So we've seen that it's moving to the right and moving to the right. So it's moved to the right a total distance of 75 meters, and then it comes to rest. And now because we've got negative velocities, it's now moving to the left. So it's now moving to the left 9 plus 42, so 51 meters. So what's actually happening here, our first section, it's moved to the right 50 meters, and it's moved to the right again 25 meters. It then comes to rest, and now we're going to move back to the left because it's a negative velocity. So it moves back 9 meters and then 42 meters. So what we're looking for here is our displacement is the straight line distance from our very start to our very end. So it's this little bit here. So what that means that we can do is to work out our displacement is that we can do 50 plus 25, so that's our 75 meters to the right. And then we take away the bits where we're moving to the left, so 42 and 9. So we're taking 51 metres away when it's moving to the left. So that gives us a displacement of 24 metres. So it's pretty cool this. Even though we've got a velocity time graph with some negatives, we can actually get more information from this, even though it looks a little bit trickier. So I hope that was helpful today. What we've done, of course, is we've looked at how we can handle straight lines with velocity time graphs. We've seen that gradients are equal to accelerations and that area between the line and the x-axis is equal to the distance travelled. Now in the next lesson, we're going to see that obviously cars don't normally just travel with a constant acceleration. So what we'd see with this, if we're plotting a velocity time graph, is some curves. So we're going to see how we can extract information from curves. Please do have a look at some of the other videos as well. I've done one recently on distance time graphs, and I hope this has all been very helpful today. See you soon.